2026 Parallel Symposium section on environmental mentoring. My name is Xinlan Huang, a master's student in the Department of Biotechnology at National Zhongxin University, Taiwan, and it is my pleasure to serve as the session chair for this afternoon. Before we begin, I would like to do a quick roll call for our presenters. When I call your name, please kindly turn on your microphone and camera, say hello, and make sure your presentation file is ready for screen sharing. Our first presenter is Mr. Muhammad. Please turn on your microphone and camera. And your microphone. Can you open the microphone and share your PowerPoint to let me know you can share it? Right. Okay, we can wait for our first speaker later. So our second speaker is Mr. Dimas. Can you turn on your microphone and camera, say hello, and share your presentation file right now? Is my microphone open?
So anyway, oh yeah, I think it's the problem of your microphone. So anyone can hear my sound or no? Okay. Good afternoon, everyone. So in here, I want to make sure about our device. Anyone have the problem with the Zoom meeting? So maybe I will ask from because I saw Salwa Ashifa. Uh, can you hear my voice or no?
Okay. Can you hear my also it's okay. So Dimas, can you share your microphone and say hello to our other participant and share the presentation files to us right now?
Yes.
Dimas, Dimas and Sanjaya already answered.
So okay. So our speaker is Dindam. Can you turn on your microphone and say hello to make sure your presentation file is ready?
Yes, I'm ready.
Thanks to Dimas, I will call you later. So I want to make sure our Mr. Dimas electric device is okay. So can Mr. Dimas turn on your microphone and say hello to our other participant? Okay, so thank you for everyone. Before we start, I would like to remind all presenters that each presentation is allocated 12 minutes. I will give a reminder when 2 minutes remain. I will open my microphone to tell you 2 minutes left. When your presentation time is up, I kindly ask you to conclude your presentation. For participants, if you have any questions during the presentation, please type them in the chat box and save them for the Q&A section. Without further delay, let us begin with our first presentation. So our first presentation, first speaker will be Mr. Dimas. And his presentation is entitled is a multi-source geospatial deep learning framework for mapping agro-industrial reduce potential for biomass-derived carbon nanomaterial production. Please join me welcoming Mr. Dimas. So, Mr. Dimas, you can speak in right now.
Good afternoon. My name is Dimas Bangkit Sanjaya. I am visit to present carbon map, Geospatial artificial intelligence project for mapping agro-industrial residue potential as feedstock for biomass. Derived carbon nanomaterial in West Java, Indonesia. The project integrates remote sensing, agricultural statistics, machine learning, deep learning, and interactive web dashboard. The main motivation is that agro-industrial residue are promising renewable carbon source. However, their spatial distribution and suitability are not always clear. Carbon map addresses this issue by converting scattered data into spatial intelligence that can support sustainable carbon material development and regional planning. The key challenge is not only estimating how much residue is available, but also identifying where it is located, how accessible it is, and whether the surrounding spatial conditions are suitable. Conventional tabular statistics are useful, but they do not directly answer spatial decision-making questions. To respond to this gap, we developed carbon map and it integrated geospatial solution. The framework combines multi-source data, a weighted suitability index, machine learning prediction, deep learning segmentation, and web-based dashboard. The first objective is to build a 1 km suitability map for West Java. The second objective is to make the result accessible to an interactive platform. The dataset include agricultural production statistics, administrative boundaries, Sentinel to spectra indices. First, next time lag and cover data, measure roads, and agro-industrial facility points. This data were harmonized into 370-937 grid cell transferring 27 districts and cities in West Java. We also use validated agro-industrial facility point to represent processing accessibility. The modeling architecture consists of three main components. First, a rule-based suitability index was created using residue potential, facility proximity, for accessibility, next time lag, profile ratio, and environmental suitability. Second, machine learning models were used are predictive baselines. Third, unit and deep-level fit reflex were applied to learn spatial suitability patterns from raster-based geospatial features. The validation stakes show that the models can reproduce the spatial structure of the proxy suitability labels. The result indicates consistent spatial patterns, strong agreement between predictor and suitability classes, and good generalization, especially for clearly sparsely suitability categories. Quantitatively, the machine learning model has achieved strong performance for suitability prediction. For the deep learning stage, unit achieved the best segmentation result with a macro F1 score of 0.933 and a mean IOU of 0.876. The fit reflex also performed well, but slightly below UNet. Is confident that UNet was more suitable for the current geospatial segmentation test. The qualitative comparison for to sports the quantitative result, the rule-based machine learning and UNet maps show coherent spatial patterns. The confidence map also helps us understand where the model is more certain. Most confusion occurs in transitional zones, while very low and very high suitability area and easier to distinguish. The final output is the carbon map with dashboard available at carbonmap.unlif.id. The web platform allows users to explore the suitability layers, compare model output, inspect special features, and interact with the map. Technically, the front end was deployed using Next.js on Vercel. When geospatial outputs were preferred as GeoJSON file terms and include optimized geotips for scalable web mapping. In summary, Carbon Map demonstrates that geospatial AI can connect agricultural residue data with sustainable carbon material planning. The framework provides not only predictive results, but also suitability, reproducibility, and a practical interface for communication and the education support. To support transparency, the project is organized for data and code availability. The repository contains notebooks, script, documentation, tables, slide figures, and web implementation guidance. The geospatial files and model way can be stored separately and that are saved as Zenodo, OSF, or Figshare. To conclude, Carbon Map shows how Geospatial AI can transform agro-industrial residue into strategic information for sustainable material innovation. Thank you for your attention. I welcome your question and feedback.
Thank you, Mr. Dimas, for your presentation. Our second speaker is Mr. Dindam for Indonesia. Today, he will present a machine learning framework for electric noise sensor response modeling toward real-time food quality monitoring and smart packing application. Please join me in welcoming Mr. Dindam. Mr. Dimas, can you close your sharing screen right now? Can you hear me, Mr. Dimas? Can you close your sharing screen?
Gimana? Jadi,
Dindam, Mr. Dindam, are you here now? Can you open your microphone,
gimana Pak Ji?
please?
Oh, share. Stop share ya Pak.
Dindam, can you share your presentation file right now and share your speaking to us? And make sure you open your camera with our Zoom background.
Oh, I'm sorry.
So, Mr. Dindam, you can speak
Good
right now.
afternoon.
Thank you.
I am pleased to present Prestech, a machine learning based electronic nose project for a real-time food quality monitoring and smart packaging application. This work uses public electronic nose data for beef, quality monitoring and develops a complete fifth line from sensor pre-processing, model training, explainable AI, and dashboard-based simulation. The main motivation is the need for rapid, non-destructive, and continuous food quality monitoring. Conventional microbiological, chemical, and sensory tests are important, but they are often slow, labor-intensive, and not suitable for continuous monitoring during storage and distribution. FreshTrack addresses this gap by converting sensor response patterns into practical quality information. The key challenge is that electronic noise signals are complex time series data. Metal oxide semiconductor sensor respond to volatile organic compound released during food deterioration. But the signal may be noisy, affected by humidity and temperature, and sometimes overlapping between quality classes. Therefore, the task is not only classification, but also robust sensor response modeling. To respond to this challenge, we developed FreshTrack as an integrated machine learning framework. The system combines signal pre-processing, smoothing, time window segmentation, statistical feature extraction, model benchmarking, explainable AI, and a dashboard simulation. The first objective is to identify food quality status from electronic noise signal. The second objective is to translate the trained model into a web-based monitoring prototype. The dataset was obtained from medley data and contained electronic noise measurement for beef quality monitoring under uncontrolled ambient conditions. It includes 10 MOS gas sensor, humidity, temperature, time series, observation, and quality labels. In FreshTrack, the raw signals are clean, smooth, segmented into non-overlapping time windows, and transformed into statistical features such as mean, standard deviation, minimum, maximum, range, slope, area under the curve, and signal energy. The modeling architecture has three main parts. First, time window features are generated from the smooth sensor signal. Second, several machine learning models are compared, including random forest, SPM, XGBoost, like GBM, and MLP. Third, the base model is evaluated using a class-wise temporal blocked validation protocol to reduce overlay optimistic result caused by time series leakage. The validation result showed that the model can detect major quality deterioration patterns, especially the spoiled class. However, early-stage quality transition remain more difficult, particularly between fresh and acceptable condition. This is except because the dataset is imbalanced and early deterioration can produce overlapping sensor response. The best performing model was like GBM using 15 minutes non-overlapping window. Under class-wise temporal block validation, it achieved 18% accuracy, a weighted F1 score of 0.826, a macro F1 score of 0.62, a balanced accuracy of 0.671, and MCC of 0.54, and macro ROC IUC of 0.839. These results are more conservative than random split results, but they are more credible for a time series food monitoring study. Explainable AI analysis saw that humidity and select MOS sensors, especially MQ4, MQ8, MQ2, and MQ7 contribute strongly to prediction. The confusion metric indicates that spoiled samples were detected reliable, while fresh and acceptable samples were more difficult to separate. This suggests that environmental factor and early quality transition must be handled carefully in real-world electronic nose application. PressTrack was also preferred as a web-based monitoring system. The front end can be implemented with Next.js and deployed on Vercel, while the machine learning backend can run using fast API on render. The dashboard simulates real-time sensor streaming, sends a raw sensor window to backend, achieves quality prediction and confidence score, and display smart packaging recommendation. In summary, PressTrack demonstrates that machine learning-based electronic nose modeling can support scalable and interpretable food quality monitoring. The main contributions are end-to-end modeling of the line, temporal validation, explainable AI interpretation, and a dashboard-ready deployment. The main limitation is that the study used a public data set and simulate real-time streaming, not a physical sensor prototype. To support transparency and reproducibility, the project is organized for data and code availability. The repository can include the clean notebook, process table, slide figures, model metadata, environment files, and documentation. The raw data set should be accessed from the official Mendeley data source, while a public repository or data archive can be used to share reproducible outputs. Okay. To conclude, PressTrack saw how electronic nose signal and machine learning can be transformed into practical food quality intelligence for smart packaging and real-time monitoring application. Thank you for your attention. Well, I welcome your question and feedback. Thank you.
Thank you, Mr. Dindam, for your presentation. Please close your sharing screen and let us welcome our second Third speaker is Mr. Muhammad. Please share your screen and open your microphone and make sure your camera's on with our Zoom background, please. Mr. Dindam, please close your sharing screen right now, please. And yeah. Mr. Dindam, can you close your sharing screen? So, Mr. Muhammad, please sharing your speaking right now. And please, Mr. Muhammad, mute your microphone, please.
Hello, good
You
morning.
can speaking now, Mr. Muhammad.
Good afternoon. My name is Muhammad Ijlal Senja Pratama. I am pleased to present HydroSafe, a digital twin artificial intelligence project for detecting heavy metal contamination in water using carbon nanomaterial sensor response modeling. The project combines electrochemical sensor data, machine learning, deep learning, regulatory threshold, and a web-based decision support dashboard. The main motivation is that heavy metal contamination in water is resistant, toxic, and difficult to remove once it enters the environment. This issue is important for human health, agriculture, livestock, irrigation, and agro-industrial processing. Conventional laboratory methods are applied, but they are often expensive, slow, and not always suitable for rapid monitoring. HydroSafe addresses this gap by transforming sensor response data in interpretable water safety information. The key challenge is not only detecting whether a contamination exists. We also need to estimate the concentration, identify the possible metal type, and interpret whether the concentration exceeds a recognized safety threshold. Electrochemical sensor response can be complex because they are affected by impedance, phase, charge transfer resistance, capacitance, pH, temperature, conductivity, and signal noise. Therefore, a data-driven model is needed to interpret the sensor pattern more consistently. To respond to this challenge, we developed HydroSafe as an interpretable digital twin framework. The system learns the relationship between carbon nanomaterial-based electrochemical sensor features and heavy metal contamination outcomes. The first objective is to predict heavy metal type from sensor response. The second objective is to estimate heavy metal concentration. The third objective is to convert the predicted concentration into regulatory contamination status using metal-specific guideline thresholds. The study used a public electrochemical heavy metal sensor dataset. The data include impedance and environment environmental response variables such as frequency, real and imaginary impedance, magnitudes, phase, charge transfer resistance, double layer capacitance, temperature, pH, and conductivity. After data cleaning, the workflow generate features such as impedance fraction, logarithmic transform, percent, and consign, conductance proxy, pH interaction terms, and normally charge transfer resistance. These features were used to train the classification, regression, and digital twin pipelines. The modeling architecture consists of their level. First, baseline machine learning models were trained for metal classification, concentration regression, and direct status classification. Second, stronger tabular models and stacking assemblies were evaluated, including random forest, gradient boosting, XGBoost, Leach GBM, chatboost, and stacking. Third, deep learning models, including multiplayer, perceptron, and one-dimension CNN, were trained with GPU support to make the sensor response modeling objective. The primary decision pipeline used prediction metal and predict concentration, followed by regulatory threshold mapping. The validation results show that concentration estimation is the stronger component of hydrosafe. The model can accurately learn the relationship between electrochemical sensor response and concentration value. Metal classification is more challenging because different metal may generate overlapping sensor pattern. For this reason, the final decision system is designed around concentration-driven regulatory intervention, which is more transparent than direct black box status prediction alone. Quantitatively, the best concentration regressor was CatBoost, achieving an R-squared value of 0.9820, a mean absolute error of 0.0555 milligram per liter, and a mean square error of 0.1044 milligram per liter. The digital twin regulatory status pipeline achieves 85.75% accuracy and a macro F1 score of 0.8128 for safe versus unsafe prediction. The pipeline achieves 87.00% accuracy. This result indicate then concentration estimation followed by threshold-based interpretation is a strong and interpretable approach for water contamination monitoring. The interpretability analysis show that impedance related variables are among the most influential features. Important predictors include real impedance, charge transfer resistance, impedance magnitude, and aggregate impedance feature. This is consistent with the electrochemical nature of the dataset, where metal ion interaction with the sensor surface changes the impedance response. Error analysis show that some confusion remains in metal identification and nerve threshold status categories, but the concentration regression output remains highly reliable for regulatory mapping. HydroSafe was also prepared as a web-based dashboard prototype. The front end is designed with Next.js and a clean blue-white interface. User can enter sensor value manually or upload a CSV file. The backend prediction service can return the predict metal, estimate concentration, regulatory threshold, exceedance ratio, contamination status, and safe or unsafe label. The dashboard also supports report export as a PDF, making the system useful for communication, demonstration, and future decision support. In summary, HydroSafe demonstrates that digital twin assist artificial intelligence can support incredible heavy metal water contamination monitoring. The main contribution is not only prediction accuracy, but also the integration of sensor response modeling, regulatory threshold logic, explainable features, and a web-ready system architecture. This makes HydroSafe relevant for environmental monitoring, agro-industrial, water safety education, and future sensor-based decision support. Support transparency, the project is organized for data and code availability, and repository pages contain the cleaned notebook, data access document, process table, selection figure, environment files, and reproducibility instruction. The public dataset source is our knowledge, and large or restricted asset can be destroyed separately if rated by target journal or repository police. Okay, thank you.
Thank you to all presenters for their insightful presentation. We will now proceed to the joint discussion and Q&A section. If you would like to ask a question, please briefly introduce yourself before asking your question. You may either type your question in the chat box or turn on your microphone when invited to speak. The floor is now open.
Yeah, okay. Thank you very much for your presentation today. So it's the interesting presentation. Both of this in this presentation will already talk about the uh, IoT system, right? Integrated system. So um, yeah, uh, let me resume from this. So in here have three studies that highlight the transformative roles of the artificial intelligence. So the advanced sensing technology and geospatial analytic is supporting the sustainable food and water and environmental system. And then I see in the first study, I think this one is presented by Mr. Dimas. I'm sorry if I'm wrong. Is use the utilize multi-source geospatial deep learning to identify the agro-industrial residue on the hotspot sustainable for the biomass derived the carbon nanomaterial production. It will be contributing to the circular bioeconomic development and then sustainable resourcing utilization. And then the second study is already demonstrate that how the machine learning and then the electronic nose technology can enable rapid and then non-destructive and then the real-time food quality monitoring. And then this will be supporting intelligent packaging system and reducing the food waste. And then the third study, it will be it's already introduced a digital twin of framework integrated with the deep learning and carbon nanomaterial sensor modeling for the efficient detection of the heavy metal contamination in the water, offering a scalable alternative to conventional laboratory based on the monitoring methods. So thank you very much for all to present today. And then, yeah, I still have some question for both of you. So actually, I'm in the first, I am interested with the electronic nose because actually my research in the future, not in the future, but start from now, I am trying to use the electronic nose to detect the pests. But in this study, the electronic nose technology will use for detecting the food quality. So this is a good presentation, but I still have some question for Mr. Dindam. So are you still in the Zoom meeting, Mr. Dindam?
Yes, sir. Yes,
Okay.
sir. I'm here.
Yeah. Thank you very much. So I want to ask about the model was developed using the public beef quality dataset. How well do you expect the framework to generalize to other food products like fish, poultry, fruit, or vegetable, which may produce very different volatile organic compound or VOC profile based on your experiment? Sorry, Mr. Dindam, you still on the mute. So please unmute your microphone first. So you're still in the mute. So please unmute your your.
Yes,
Okay,
sir.
yeah,
I'm
it's good.
sorry. I'm sorry.
Okay, please,
Okay. Thanks for your question, sir. That is possible because a carbon-based nose can detect all types of volatile compounds. Yes.
yeah. So it will be detect on the one device, or you will use a lot of device for detecting this. Because you mentioned you use the, I think, MQ gas sensor to detect, right? And then you also collect for the humidity and then temperature also. So because like the MQ and then MQ gas sensor, they have the specific detection for the smell. So which one of the smell you detect using this? Because I think MQ will detect alcohol or ethanol. I forgot it. So please, Mr. Dindam.
For device, only one device, but one specific sensor.
Okay.
Many Many
Also,
specific sensor. Yes.
okay. Yeah.
Yeah.
And then which smell you detect for the gas sensor? Because the gas sensor have the specific detecting volatile organic compound.
Sorry, sir. Can you repeat your question?
Okay. Yeah. In your presentation, in your slide presentation, you will use a lot kind of the gas sensor, right? So, may I know which gas sensor will detect which kind of the volatile organic compound, because they have the specific volatile organic compound detection at there. For the example, I see one on your gas sensor is the MK6, and then this MK6 will be detect some alcohol volatile organic compound. So how about the other gas sensor you use for detecting this meat? Which one, which volatile organic compound will detect for this meat? Okay, maybe
We only use MQ sensor for volatile, all volatile. Yeah.
okay, all volatile. So it's not yet specific on the which one the volatile, right?
Yes, sir.
Okay, so the may I know what is the result for the volatile detection in the M key? Is the which part is the ppm or something? Okay, let me move to another speaker in here. Maybe I will ask Mr. Dimas Bangkit Sanjaya. Can you hear my voice or not? You're still on the mute, so I can't hear your voice. Mr. Dimas Bangkit Sanjaya. Okay, so yeah, I'm interested also with your presentation today. I appreciate how the study combine remote sensing and then geospatial analysis and then deep learning, right? So you combine three part of this one, and then uh, the integration of the multiple spatial data set will provide a comprehensive approach for the identify biomass, right? So from your study, the estimate residue potential using the crop production statistic and residue to product the ratio. How did you address uncertainties associated with this assumption? And have you considered validating the estimate using the field-based residue environment? Can you get my question, Mr. Dimas? You're still on the mute, Mr. Dimas.
Can
Okay.
you repeat question?
Oh, okay. So from your experiments, you will combine between the geospatial and then the AI, the machine learning, and then once again you will combine also for remote sensing, right? Is it true, Mr. Dimas?
Yes.
Okay, so my question is, in the study, will estimate residue potential using the crop production statistic and the residue to product ratio, right? In your study, you will estimate potential using the crop production statistic and then the residue to product ratio. Is it true, right?
Yes.
Okay, so how did you address uncertainties associated with this assumption, and have you considered validating the estimate using field-based residue inventories? You know what I mean? You got my question or not, Mr. Dimas? You still in the mute. Calm down. It's okay. So you have a three parameter. One is the geospatial, right? Geospatial. And then the second is about the machine learning. And then the third layer is the remote sensing. So do you make sure the result of the remote sensing with the real area? You know what I mean, right? Because remote sensing only will be predict. How about the real? So have you compare or have you make sure with the real field or with field-based residue inventories, Mr. Dimas?
So I'm just assuming based on the data of factories in West Java test product residue.
So you already check or make sure with the field data directly?
No.
Oh, not yet. Oh, okay.
No.
So it's still on the predict. Okay. So let's do the Mr. Ijal Senja Pratama. Pramata, sorry. Can you hear my voice or not? Mr. Ijal Senja Pramata, sorry. Or maybe Miss Annie Huang, do you have any question for both of the presenter in here? So maybe for the other, like Miss Salwa Ashifa, or maybe we can talk each other like with Mr. Dindam Darusalam also. So do you have the answer for my question before, Mr. Dindam? Do you get the answer or not? You can. It's okay.
So I would like to ask a question to our Mr. Dimas, and I want to ask, like, how 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 can you make sure your experience using with AI model will be correctly AI machine model will be correctly for our paper.
Yeah, so Mr. Dimas, okay. I think you're still on the mute, so you can we can hear your voice. Can you unmute first, Mr. Dimas?
Can you repeat your question?
How can you make sure you're using this AI model to do with your experiments? You think it is correct for your how can can you understand my English? I mean, you use a lot of sensors to mapping all of the industrial. How can you make sure that all of them is correct? In your experiment, I mean, some machine have when you use some machine will have some problems, and can you understand?
Okay, so I think the question from Miss Annie, she want to ask about because you both of you, I think it's not only for Dimas also, I think it's also for Dindam, Mr. Dimas, and then Mr. Ijal. So how do you make sure the result from the AI, from the machine learning or anything you use to detect of your subject, how do you make sure your result? Because like when I asked Mr. Dindam, he said the M key or the gas sensor is not yet calibrated with the with the volatile organic compound, so it's still all of the volatile compound randomly detected by the gas sensor. So how you make sure, because you don't have any parameter for this one, right? For example, if you want to detect the target smell is the alcohol, so we can know it. This is the ethanol or the alcohol is how many ppm. But in your experiment, we still don't know. So how but all of you make sure the result from the AI is accurate, because yeah, if we talk about the food, the air contamination, it will be uh, important for us. Please, Mr. Dimas, if you can answer, or Mr. Ija, or Mr.
Let
Dindam, please.
me
Okay,
answer
from
your
Mr. Dimas.
question. Because we are using official data from the West Java
Sorry.
government and Google Earth,
Uh-huh.
we're pretty confident in the result. That said, since this is just an AI prediction, there could still be some mistakes.
So it still have some mistake from your result, like your accuracy is 95% and then still have the another mistake also. Is it true?
Yes.
Okay. So how about Mr. Dindam? I think you're still on the mute, Mr. Dindam. If you want to talk, please open your maybe we can. Okay, wait. Okay. I think this is the I will try to compile all the result from our discussion today, and then I hope so it will be accepted for both of you. And then from this in this session we talk about the environmental monitoring. Collectively, the three studies underscores the increasing importance of the artificial intelligence, because both of you talk about the artificial intelligence. Advanced sensing technology, geospatial analysis to support sustainable food, water, and resource management system. This research is in line with the ISAFE 2026. The theme is the advancing sustainable innovation for food, energy, and environmental resilience, and show how digital technology can be used to enhance monitoring, prediction, and decision making across several area sustainability. In here, together, the contribution demonstrate how interdisciplinary innovation at the intersection of the agriculture, environmental science, engineering, and artificial intelligence can bolster resilient food, water, and biosource system. The finding underscores the importance of technology-based solution in foresting, sustainable development, and environmental resilience. Thank you very much for all. Please, Miss Annie, to close for this session.
Thank you to all presenter and participants for your valuable contribution and active discussion. Before we conclude, we would like to present a certificate of participation to our speakers in recognize all of their valuable contribution to this section. So I will share the screen first. And the certificate of application for our presenters in International Symposium on Agriculture, Forestry, Fishery, and the Environment. The theme is Resilient Energy, Food, and Water System for Addressing Global Crises through Sustainable and Integrated Solution for our presenter. And the first speaker for our third speaker is Mohammed, and followed by Dimas and Dindam. Thank you all for your presentation and excellent presentations. We will send this certificate after our symposiums file through the emails. As a reminder, a short break will held by 3:30 p.m. to 3:45 p.m. The best presenter and closing discussion section will begin at 3:45 p.m., followed by the closing ceremony at 4:15 p.m. Thank you once again for your participation and support. We look forward to seeing you in the next section. Have a pleasant afternoon. Thank you, everyone.
Okay, thank you very much for everyone. So please come back to the main room after from this background room. So thank you very much.
Thank you.
Mhm.
Kamu butuhin ini. Yang lain. Okay. We are just waiting in 2 minutes for everyone to go back to the main room, and we'll continue and resume for the closing session. Okay. Okay, thank you for all of the presentations today. And on the behalf of organizing committee, I would like to already on.
Yeah, this room.
In this room. Okay. Sorry. And that concludes all of the presentations for today. On the behalf of the organizing committee, I would like to extend my sincere appreciation for all the presenters for their time, effort, and valuable contributions. Your work has made the session both very engaging and intellectually enriching. Thank you for everyone. And we will now begin with a synthesis of today's symposium. To deliver the synthesis, it is my pleasure to invite Mr. Reza Fikri Al-Fatah. Mr. Reza Fikri Al-Fatah, please join us to share the synthesis. Thank you.
Thank you very much, Ms. Angel.
Mr. Reza, you are on mute.
So thank you very much for Ms. Angel. On ISAFE 2026, we have a 4-part of the symposium. One is talk about the environmental monitoring. The second one is the soil. The third one is the sustainable agriculture. And then the fourth one is the agroecology. And then collectively, from the environmental monitoring, we have the 3 studies underscores the increasing importance of artificial technology, geospatial analysis to support sustainable food, water, and resource management system. The research is in line with the ISAFE 2026 theme advancing sustainable innovation for food, energy, and environmental resilience, and show how digital technology can be used in enhance monitoring, prediction, and decision making across several areas of sustainability. Together in the environmental monitoring, this contribution demonstrates how interdisciplinary innovation at the intersection of agriculture, environmental science, engineering, and artificial intelligence can bolster resilient food, water, biosource system. The finding underscores the importance of technology-based solution fostering sustainable development and environmental resilience. The second part about soil together in this part have a three study showcase the new ways to enhance environmental resilience through sustainable management of land, water, agricultural resource in line with the ISAFE 2026 theme also. This collective contribute illustrative how sustainable technology and ecological innovation can improve resource efficiency, environmental restoration, and climate adaptation to support resilient food, water, and land system into the future. The third part, this study about the sustainable agriculture. This contribution demonstrates that sustainable and resilient food, water, and environmental system require collaborative governance, adaptive organization, and empowered community, providing valuable insight for addressing climate and sustainable challenge in enhanced uncertainty world. The last one on the agroecology. This contributes to show how sustainable land management, circular use of biosource and biodiversity-based innovation can support resilient food systems and contribute to environmental and socio-economic sustainability. Thank you very much for all participation today. I will give back to the Miss Angel. Thank you very much.
Okay, thank you so much, Mr. Reza, for the synthesis of today's symposium. And now we are pleased to announce the official publication of the Symposium Abstract Book, which compiles the research abstract presented throughout today's program. We hope this publication will serve as a valuable resource for continued learning, collaboration, and academic exchange among all participants. We will be giving copies to the National Chongqing University, Taiwan, to Veteran Yogyakarta, Indonesia, to Borneo Tarakan University, Indonesia, and to Bangkit State University in the Philippines. We could start with the abstract book. We'll be giving it to Mr. Reza again.
Is representative from UPN Yogyakarta to receive this proceeding book from us. This one is the one collaboration between the NCSU National Chongqing University with the UPN Universitas Pembangunan Nasional. So the second one is for National Chongqing University. I'm sorry. Professor Lu, please come because this one is our product from our symposium, and then this one I will give to the IDPA because IDPA. Thank you. Okay, so Bangkit State University, Mam Ronda,
Okay, thank you so much, Mr. Reza, for all of the abstract book. Now we're going to awarding the certificates to our on-site participants. Please welcome to our on-site participants to come up front. We will give out our certificates and take a photo together. Thank you. Okay, for giving out the certificates to our on-site participants, let me invite Dr. Rhonda Tulai and Professor Love to come join us in front and give out the certificates for our on-site participants. Please come up front. Okay, please join us, Mr. Muhammad Sufian from National Chongqing University, country of Pakistan. Please welcome Mr. Muhammad Sufian. And next one, please let me invite Mr. Ahmed Mahmoud.
Thank you.
Thank you, Mr. Muhammad. Let me invite Mr. Ahmed Mahmoud from National Chongqing University, country of Egypt. Yarrow. 有啊，下面的。是有两个，对啊，是 author 或者是 presenter， 对，对啊，我有，我这个有 Q 啊，有。是了，我也不懂。Okay, thank you, Mr. Ahmed. And next one will be welcoming Ms. Jane Hillary from Indonesia. We'll skip that, and it will be Ms. Ratnasari Listianingrum from Indonesia and National.
Still in the lab. Next one.
Mr. Ahmad Rohib Mabrur.
Yeah.
Ms. Karunisa from Indonesia, National Chongqing University.
Yeah. 1, 2, 3.
Okay, thank you, Ms. Karunisa. And next one will be welcoming Mr. Erfan Dani Saptia from Indonesia, National Chongqing University. Next one will be welcoming Ms. Sugiyati Ningrum from Indonesia. Mr. Reas Mahamud from Bangladesh, from Department of IDPA, National Chongqing University.
And he is very loyal.
Yeah.
He is a pet. 1, 2, 3. Okay.
And last one would be Senja from Singapore, National Chongqing University.
He's
Miss
already gone.
Senja from Singapore.
He is already gone.
Okay.
Of the presentation.
And then
Orang itu sih kan.
skip. And we're all done for the on-site participants. We are now moving on to presenters. We are now moving on to the presenters, on-site presenters.
So that's not. Yeah, yes,
We are now calling our on-site presenters to give out the certificate to Mr. Ahmed Muhammad Mahmud Ahmed.
I am a high school. I'm so speaking. One, two, one more. Small.
Committee now? We're doing committee. So yeah. Please welcome Ms. Sukiyati Ningrum from Indonesia, Department of IDPA, National Chongqing University. Please welcome Ms. Sukiyati Ningrum. Do we have more for presenters and on-site? Everything is done? Okay. For our online presenters, speakers, and participants, please don't forget to do the QR code for the feedback so you can get your own certificates. It will be emailed to you later on after we finish the symposium. And kindly accomplish the feedback again from posted in the chat box. And once again, congratulations and thank you to all others and presenters for their contribution. And next, it is my honor to invite Professor Law to deliver the closing remarks. You can stay in the front.
So, yeah, good afternoon to all the respected speakers.
Yeah.
Okay, thank you.
Thank you so much, Professor Law, for the very insightful closing remarks. And before we finish with our symposium, I would like to invite everyone online to open your camera, and we'll do a photo session before we finish. Please, everyone, if it's possible, could you please open your camera for all of our participants online?
Okay, just the first frame first. Please give me enough time for the screenshot. The others can also take their screenshots. Thank you. Next frame, so that everyone's faces can be seen. Please just open.
Reminding everyone to please open your camera. We are
Okay.
now doing a photo session for the online participants. Okay, everyone's good? Okay. Now it is time for me to invite all of our on-site participants, other speakers, committee, and professors to come up front. We'll do a photo session before we finish. Thank you. Please come up front for everyone who is here on site.
We can discuss.
Maybe two lines, maybe two liner. Yeah. Pizza, join.
It's okay, Mom. It's okay, bro. First. It's okay, Mom. It's okay, bro. 1, 2, 3. Maybe Nini, you can move to the left side because I cannot see your face. 1, 2, 3. Once more. 1, 2, 3. Thank you.
You invite all the committee members.
Yes. Yeah. So before we do the closing remarks, please, I will invite all of our committee members who join us today.
Whole class.
Mr. Reza, Ms. Maisa, Annie, Yarrow, Cherry, and Hohang. Okay, please come up front so we can give out the certificates and take a photo session. Thank you.
You can distribute the certificates. Professor.
And for all of our on-site participants, before we close the symposium for today and before you went out, please give back your card and name tag. Please give it to us up front. Thank you.
What about Tehang? Tehang has it? Yeah, so that one.
Maybe you can move to more middle. Yes. Nice. 1, 2, 3. Your face, Yarrow. Okay, nice. 1, 2, 3. Maybe another. Host any other one? Okay. Look first. 1, 2, 3. Thank you. 1, 2, 3. Very nice. Okay, thank you. Congratulations. Okay, thank you so much for all of your hard work for today, to all of our committee and Professor, Mrs. Kara and Mrs. Rhonda. Thank you so much for your hard work and participation for today. And thank you for all the enthusiasm and engagement throughout today's symposium. It has been a very privilege to have you here with us. We hope that today's discussion and presentations have been both meaningful and inspiring. On the behalf of the organizing committee, I would like to extend my sincere appreciation to all presenters for their time, effort, valuable contributions. Your work has made the session both very engaging and intellectually enriching. Thank you once again for joining us, and this concludes today's symposium. For all the on-site participants, we wish you a safe journey home and have a wonderful rest of the day. This has been a wonderful experience for all of us to welcome you to today's symposium. And before signing out, I'm Angelina Natalia Lim from Department of International Bilateral Program of Agriculture, National Chongqing University, your host for today's symposium, ISAFFE 2026. Thank you. For all of our online participants, you may now leave the room. We are finished for today's symposium. Thank you so much.
Thank you. See you next time. Terima kasih Mas Reza. Sukses. Terima kasih. Assalamualaikum. Izin live.